Hello everyone, I hope you guys are doing extremely well. Today we are going to discuss an important problem in our binary search tree series. The problem name is largest number in BST which is less than or equal to n. It is also called find floor of n. Okay, so let's understand the problem description first. So we are given a binary search tree and a number n. Now our task is to find the greatest number in the binary search tree which is less than or equal to n. Now if the value of this element exists, in that case we need to print that value, and if all the values are greater than this n, in that case we need to return -1. Okay, so let's take a quick example to understand the problem description more clearly. So let us say we are given the root node of the binary search tree as node 25. Now the left child of node 25 is node 15 and the right child is node 35. Now for node 15, let's say the left child is nothing but node 5 and the right child is node 20. Now for node 35, the left child is null and the right child is node 45. We are given n as 26. Now for n is equal to 26, what is the largest value which is present in this binary search tree that is less than this number? Okay, so can 25 be the answer? So 25, yes, 25 is less than n. Okay, so 25 can be the answer. I'm not, as of now I'm not sure. Okay, so 25 can be the answer. Can 15 be the answer? Yes, 15 is less than or equal to n. Okay, so 15 can also be the answer. Now what is the maximum of 25 and 15? The maximum of 25 and 15 is 25. So obviously 15 cannot be the answer because we want to find the largest number that is less than equal to n. So the largest number that is less than or equal to n is nothing but 25. So for this case the output will be nothing but 25. Okay, now let us say we are given a number 60. So in this case, as you can clearly see, the largest number that is present in this binary search tree which is less than 60 is nothing but this node 45, this value. So node 45, for node 60 the value is nothing but node 45. Now let us say we are given n as 2. Now as you can clearly see, we have all the nodes present in this binary search tree which is greater than n. So there is no value which is present in this binary search tree that is smaller. So for this case we are just going to return -1. Fine. I hope the problem statement made sense to you guys. So now we are going to understand how we can solve this problem. So let's take an example to understand it. So let us say we are given the root node of the binary search tree as node 28. Now the left child of node 28 is, let's say, node 19 and the right child is node 32. Now for node 19, let us say the left child is node 7 and the right child is node 25. Now for node 7, the left child is null and the right child is also null. For node 25, the left child is, let's say, node 22 and the right child is node 26. Now for node 32, the left child and the right child is also null. So now we are given n as 24. Okay, and we want to find the largest value which is less than or equal to n. So how can we solve this problem? So the brute force approach, like if you are sitting in a coding interview, the first approach that you should tell to the interviewer will be the brute force approach. Now what is the brute force approach of solving this problem? The brute force approach can be just do an in-order traversal of this binary search tree, and we know the in-order traversal is going to give us a sorted array. Now once we have the sorted array ready, we can just find out which value is largest and is less than or equal to n. So let me explain what do I mean by this. So let me do an in-order traversal. So in-order traversal is nothing but processing the left subtree first and then processing the node and then processing the right subtree. So I have already made a video on in-order traversal. I will request you guys to please check out that video. So what we are going to do, we are going to start from the root node. So for root node, is there any left subtree? Yes, the left subtree is node 19. So we'll reach at node 19. For node 19, is there any left subtree? Yes, the left subtree is node 7. So we'll reach at node 7. Okay, now for node 7, is there any left subtree? There is no left subtree. So now we are going to process the node. Processing the node means adding the value of this node in an array. So let's say we have created an array in the beginning and we are going to add the value. So 7 will be added. Now, is there any right subtree for node 7? There is no right subtree for node 7. So now we can simply return because we have processed everything. So for node 19, we have processed the left subtree and now we are going to process the node. So processing the node means adding this value. So 19 will be added in our in order array. Okay, now we are going to process the right subtree of node 19. So the right subtree of node 19 is node 25. Okay, so for node 25, is there any left subtree? Yes, the left subtree is node 22. So we'll reach at node 22. Now for node 22, is there any left subtree? No, the left subtree is null. So now we are going to process the node. So how we can process the node? We can add the value of this node in the array. So 22 will be added here. Okay, now is there any right subtree for node 22? There is no right subtree for node 22. So we are simply going to return from here. Now for node 25, we have processed the left subtree and now we are going to process the node. So how can we process the node? We can add the value of this node. So 25 will be added here, right? And now we can process the right subtree of node 25. So the right subtree of node 25 is node 26. We'll reach at node 26. Now for node 26, is there any left subtree? There is no left subtree. So now we are going to process the node. So processing the node means adding the value of this node. So 26 will be added here, right? Right, now is there any right subtree for node 26? There is no right subtree for node 26. So we simply going to return. Now for node 25, we have processed the entire left subtree, we have processed the node, and we have processed the entire right subtree. So we simply going to return. Now for node 19, we have processed the entire left subtree, we have processed the node, and we have processed the entire right subtree. So we simply going to return. Now for node 28, we have processed the entire left subtree. Now we are going to process the node. So 28 will be added in our array. And now we are going to process the right subtree. So the right subtree is node 32. So we'll reach at node 32. Now for node 32, is there any left subtree? There is no left subtree. Fine. Is there any right subtree? So is there any left subtree? There is no left subtree. So now we are going to process the node. So 32 will be added in our array. Right. Now is there any right subtree? There is no right subtree. So we simply going to return. Now for node 28, we have processed the entire left subtree, we have processed the node, we have processed the entire right subtree. So we simply going to return, and that's it. Once we are done with the inorder traversal, what we can do, we can just traverse this array. So how can we do that? We can check, okay, the first value, that is the 7 is less than 24. So 7 can be the possible answer. So answer will be updated to 7. Initially answer is nothing but -1. Now answer will be updated to 7. Okay, now the next value is 19. Okay, 19 is also less than equal to 24. So what we can do, we can change our answer to current value. So it will become 19. Okay, because it is the largest value, and since the array is increasing, so we are going to get a large value. Okay, now the next value is nothing but 22. Now 22 is less than n. Yes, 22 is less than 24. So answer will be updated and it will become 22. Now the next value is 25. That means 25 is greater than n. And now we don't need to go further, because now we know that all the values after this will be greater than n, because the current value is greater than. So here we are just simply going to return whatever the value that will be stored in our answer. So here the answer is having a value 22. That means for n is equal to 24, that's the largest value that is less than or equal to n present in this binary search tree is nothing but 22. Okay, so the value is 22. Now talking about the time complexity of this approach, the time complexity of this approach is big O of n, because we are doing an inorder traversal of the binary search tree, and to do an inorder traversal we have to touch every node. So the time complexity is big O of n, where n is the number of nodes present in the binary search tree. And the space complexity is also big O of n, because we are creating an array, extra array, to store our answer. Okay. Now, if you are sitting in a coding interview, the interviewer will not be pleased with this time complexity and the space complexity. It is good, it is linear, but we are not utilizing the property of the binary search tree. What is the property of the binary search tree? That the property is the left subtree is going to have a smaller value and the right subtree is going to have a larger value. So we are not utilizing this property. So let's understand how we can utilize this property to bring down our time complexity to logarithm in the average cases. In the worst case, it will be big O of n. But in the average case, we can bring down the time complexity. So let's understand how we can do that. So let's take an example. Let us say we are given the root node of the binary search tree as node 68. Okay. Now for node 68, the left child is node 20 and the right child is node 78. Okay. Now for node 20, let us say the left child is node 15 and the right child is node 30. Now for node 15, the left child is null and the right child is node 18. For node 30, the left child is null and the right child is node 40. Now for node 78, the left child is node 70 and the right child is null. Now we want to find the given value of n is nothing but, let's say, 29. Okay, now we want to find the largest value that is less than or equal to n present in this binary search tree. So what we can do, we can always start from the root node, right? Now we can start from the root node. Now 68 is greater than n. That means we don't need to process the right subtree, because if we are going to process the right subtree, then we are going to get a larger value. We are not going to get a smaller value, right? So now from 68 we can say now we are going to process only the left subtree. So now we'll reach at node 20. Okay, now for node 20, node 20 is less than or equal to n. So node 20 can be an answer. So we can store this answer of node 20 in some global variable. So initially global variable was -1, and now we have updated to it to 20. Okay, now for this 20, we can clearly see that this 20 is less than n. That means we should not go in the left subtree, because if we will go in the left subtree, then we are going to get a smaller value, right? And since we wanted to find the largest value for n, that is smaller, we have figured out that 20 can be the largest value in the left subtree. So now we should go only in the right subtree. So from node 20 we'll reach at node 30. I hope this is clear to you guys. So we'll reach at node 30. Fine. Now once we reach at node 30, we can say okay, node 30 is greater than node 29, right? That means this value, this 29 value. So now we should visit the left subtree. Now for node 30 there is no left subtree. That means we are done, and we can clearly see the answer is stored in our answer array. For n is equal to 29, the answer is nothing but 20. 20 is the largest value that is less than or equal to 29. So let's take one more example. Let us say we are given n as nothing but 19. Okay, so how can we solve? So first of all, we are going to start from the root node. So the root node is having a value 68. Okay, now answer is initially set as -1. So now 68 is greater than n. That means 68 cannot be the answer, because we want to find the small value than n. So 68 cannot be the answer, and we should not go in the right subtree of 68. So now we should go in the left subtree. So we'll reach at node 20. Okay, now for node 20, we can again see that okay, 20 is greater than 19. 28 cannot be the answer. So sorry, 20 cannot be the answer. So what should we do? We should visit the left subtree only. So from node 20 we reach at node 15. So now we reached at node 15. Okay, now for node 15, 15 is less than 19. So 15 can be the answer. So answer will be updated to 15. So it will become 15 now. Okay, now what we need to do? Which side should we move? We should move to the left side. Why? Right side. Why we are moving the right side? Because we have find one value which is less than or equal to n, and now we don't want to find any more smaller values. We want to find larger values if possible. So now we'll move to the right side. So we'll reach at this node 18. Now for node 18, we can clearly see 18 is less than 19, so it can be the answer. So answer will be updated to 18. Okay, now for 18, which side should we move? We should move to the right side, and there is no right side, so we are simply going to get our answer as nothing but 18. Okay, but now if you carefully observe, the time complexity has been reduced to big O of log n, because at every point we are just discarding the entire left subtree or the entire right subtree. So the time complexity has been brought down to logarithm, and we are not creating any extra array. So the space complexity can be treated as constant, that is big O of 1. I hope this made sense to you guys. Space complexity is big O of 1 if we are not using any extra array, but the space complexity will be big O of log n for the recursive stack space. Okay, so you can explain it to the interviewer, both the two things. Okay, I hope this approach is clear. Now we are going to understand how we can implement our logic in the form of code. So let's do that as well. So as you can clearly see, I have already declared a function called findFloor that is taking the root node and a number n as an argument. Root node is nothing but an object of class tree node. A class tree node is having a constructor that is initializing the value of the node. The left and the right child of any node is by default set as null. So now what we are going to do? The first thing that we are going to do is to initialize a global variable. So let's call that global variable as answer. So answer is initially set as -1. So why I am declaring in the form of a list? Because I'm going to pass this answer in my recursive function, and I want this answer to get updated at every recursion and not lose its originality. So now I'm going to create a recursive function. So let's name this function as findFloor. I can also let's name this function as find floor util. Pass the root node, pass the value of n and the answer. Now after this I just need to return whatever the value stored in this answer array, so return answer of 0. So let's write this function def find floor util, and we have root, we have n, and we have answer. Okay, so now if the node that I'm currently on, that is if root is none, in that case I need to simply return. The first thing is that if the current node that I am on is null, in that case I cannot do anything, so I just need to return. Now what is the second thing? The second thing is if root dot value is greater than n, that means the current value that I am on is greater than n, and in that case I just need to move in the left subtree. So I'm just going to move in the left subtree. So find floor util, okay, root dot left and then n and then answer. Okay, now else means the second part. So in the second part what I need to do, I need to update my answer first. So answer of 0 will become equal to root dot value. Right. Now after this what I need to do, I need to make a call for the left subtree. So let's call for the left subtree. So find floor not the left subtree, the right subtree. So find floor util root dot right, pass n and then pass answer, and after this I just need to return, and that's it. That's all about the code that we needed to do. So let's take a quick example to run our code. Let us say we are given the root node as node 15. Okay, now the left child of node 15 is nothing but node 5, and the right child of this node 15 is nothing but node 18. Now the left child of node 5, that is root dot left is nothing but node 2. Now given the value of n is nothing but, let's say, 4. So let's check what is the output for this code. So print find floor, pass the root node and pass the value of n. So let's give this function a run and let's check the output of our code. So the output of the code is coming out to be 2, which is absolutely correct, because for 4 the only value which is smaller than or equal to n, which is nothing but 2. So I hope the code made sense to you guys. If you guys still have any queries regarding this problem, please drop your concern in the comment section and I will be more than happy to help you there. Regarding this series, I will be uploading more of the questions in the upcoming week, so keep following us. Until then, keep smiling and keep coding. Thank you.